Welcome to section 11.7. This is the 109th session of the CISSP exam prep series. In this session, we'll get concrete about the protocol that addresses every packet. We'll answer several questions. What does the Internet Protocol itself do? How do the two versions of it differ? How does the newer version hand out addresses? What are the security concerns during migration? How do the classic address classes and modern notation work? And what do the two helper protocols add? Why does this matter beyond the exam? Because addressing decisions shape your filtering, your monitoring, and your attack surface. Imagine your organization begins enabling the newer address version on production systems. If your security tools cannot see that traffic, you have just opened a blind spot. Knowing how addressing works and how the two versions coexist is what keeps that transition from becoming a gap an attacker walks through. So what does the Internet Protocol itself do? It provides root addressing for packets, and that addressing is the foundation of global communication. It gives every packet an identity and prescribes a path, but notice its personality. It is connectionless and unreliable. It does not promise packets will arrive in order, or arrive only once. It simply makes its best effort to find a route, even across a damaged network. That is why you pair it with the reliable transport protocol on top. Think of a determined courier who always tries a route but signs no guarantee. How do the two versions of it differ? Mainly in address size and built-in features. The older version uses 32 bits for addresses, while the newer one uses 128, a vastly larger space. The newer version also brings features the old one lacked, such as scoped addresses for grouping access, automatic configuration, and quality of service priorities for managing traffic. And where the older version treats security as a bolt-on, the newer version has the security suite built in. Picture upgrading from a small numbering scheme that ran out of room to one with practically endless addresses and modern conveniences baked in. How does the newer version hand out addresses? In two ways. Its updated configuration service can run in a stateful mode, assigning specific addresses and tracking them, much like the classic service did. Or it can run stateless, providing configuration details without assigning addresses, leaving devices to build their own. In that self-assembly, routers periodically advertise the network prefix, and each device combines that prefix with an interface identifier often derived from its hardware address. For privacy, some devices randomize that identifier instead. The result is a unique address the device assigns to itself. It is like a building announcing its street, and each resident forming their own apartment number from it. What are the security concerns during migration? Two big ones. First, the enormous address space means attackers have far more source addresses to rotate through, so simple address block lists become much less effective. Second, and more dangerous, is a monitoring gap. If you enable the new version before every security and monitoring product fully supports it, that traffic flows unwatched and unfiltered, effectively a covert channel. Both versions can coexist through a few methods, running both stacks at once, tunneling one inside the other, or translating between them. And a cautious organization can start at the edge, supporting the new version only on internet-facing devices. Upgrade your visibility before you flip the switch. How do the classic address classes and modern notation work? The older addressing was first organized into classes by the value of the first octet. The early classes offered progressively smaller networks, with additional ranges reserved for multicasting and for experimental use. A couple of ranges were set aside for special jobs, such as the loopback address a machine uses to talk to itself. But rigid classes wasted addresses, so the field moved to a flexible system. Classless notation writes the network size as a simple slash count after the address, letting you size subnets precisely and combine ranges. Think of switching from a few fixed box sizes to made-to-measure packaging. What do the two helper protocols add? Health checks and group delivery. The control message protocol reports on the health of a network or link, and it powers familiar tools that test whether a remote system is reachable and how well the path performs. Because its features were abused in bandwidth flooding attacks, many networks now limit or throttle it. The group management protocol supports multicasting, the delivery of data to a specific set of recipients at once. It manages which hosts belong to a multicast group, and a single stream can be duplicated at a router only where paths diverge. Think of one announcement copied only at the hallways where audiences split off. So let's bring it together. The Internet Protocol addresses and routes packets on a best effort, unreliable basis, which is why you layer the Reliable Transport Protocol on top. The newer version dwarfs the older one in address space and bakes in features and security. It assigns addresses statefully or lets devices self-configure statelessly. Migration raises real concerns, especially unmonitored traffic, so extend visibility before enabling it. Classic classes gave way to flexible, classless notation, and the two helper protocols add health testing and multicast group delivery, master addressing, and you control both where traffic goes and who can watch it. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.